The memory system in any computing system or motherboard or computer motherboard obviously is not unlimitedly fast and not unlimitedly large. There are limits in the amount of memory, and there are limits on how fast we can read or write to it. So how can we improve this performance? Memory, as the main component in a computing system, oftentimes could not meet the microprocessor's specification. Either it is too slow to cope up with the current microprocessor speed, or it is too small to load the entire modern code and modern multimedia data. Multimedia data, for example, video, is really large, and oftentimes it cannot be loaded entirely into the memory system. Some smart workarounds has been done to solve these problems. To solve the speed problems, memory caching scheme was invented. To solve size problems, memory virtualizing is a scheme that was invented for this. We can view this solution this way. We have the regular microprocessor and then the regular memory system. To solve the speed, we put in between the microP and the memory system what we call cache memory. The reason is because this is a fast memory. This is not as fast, but the size is larger. Main memory is larger than the cache memory. So fast and small is suitable for SRAM. Big but not as fast is DRAM. And to solve the capacity, we want something like unlimited memory space. We use a scheme we call virtual memory. If cache memory is between microP and main memory, virtual memory is the one that we put on hard disk, and that is what we put beyond the main memory. Let us define cache memory. Cache memory is a much smaller piece of memory than the main memory, but much faster. That is used to temporarily keep the content of the main memory where the microprocessor will be accessing, instead of directly to or from the main memory. That is basically the meaning of cache. Content from the main memory will be loaded into cache on demand by the microprocessor. Since cache memory is smaller, we can only keep a small portion of main memory in it. We subdivide the cache memory into slots. One slot can keep one portion of the main memory. We call it slot in cache memory. In the main memory, we call it block. Because of this, there is a need to keep track which part or which block of main memory is being kept in the cache slot. This process is what we call mapping. So this is the complication that we have to add when we solve the speed of main memory. We use cache memory to solve the speed problem with main memory, but now we have an overhead to map which part of the cache memory is actually coming from which part from the main memory. Definition: mapping scheme in cache memory is the scheme whereby we relate or link which slot in the cache is holding which block, which part or which block in the main memory. There are three mapping schemes. First is associative mapping. Second is direct mapping. Third is set associative mapping. Associative mapping is the kind of mapping that the cache system will allow any block in memory to be kept in any slot in the cache. The relation or the link from the main memory to the cache is resolved by having some tags. The MSB part of the address that we use to issue to read to the main memory is used as tags. The LSB part is used to address which word in the slot that we are looking for. For example, this is a memory system with 32 bits address line. This memory caching system is having 27 bit as tag, the more significant 27 bit. The remaining 5 bits is to address which word in the cache that we are looking for. In this case, this cache system have 32 words in one slot, 2 to the power of 5. And it has 2 to the power of 27 number of blocks. This can be seen in this next slide. This is the cache system. The 27 bits of MSB in the address is used to choose which block in the memory. And you can see here, it's written there, per block there are 32 words. But you can see here, the number of slots in the system is a lot less than the addressable memory area in the memory system. There's supposed to be 2 to the power of 27 number of slots. If, let's say, we are making a system, a cache system that is mapping one-to-one to the memory system, we should have 2 to the power of 27 number of slots. But doing that actually defeats the purpose of having a small amount of memory, which is fast, that we call cache memory, which we might as well use the cache memory as the main memory. So the number of slots should be a lot less than the number of blocks that we have in the main memory. As we mentioned a few times, cache system is a smaller memory system but faster. So there are times when it is full. In that case, we need to flush or empty content of certain slot so that we can reload with new blocks in the main memory. And on top of that, with associative mapping scheme, where we allow any block of the memory system to be kept in any slot of the cache system, we have to find a way, a proper policy, so that we can find the best slot to be flushed when replacement has to be done. This policy is what we call replacement policy. There are a few ways of doing replacements, or there are a few policies in replacing slots of cache memory. We can do it by LRU, least recently used, which means any of the slot in the cache system has never been accessed either read or write for the longest time. That one we can assume to be no longer in need, so we can flush it out. We can also have FIFO. This sounds like queue. When we add the blocks of memory from the main memory, we round robin which slots to be filled in the cache system. We can also use the scheme LFU, least frequently used. We can consider this like the slot in the cache memory that is most unpopular. So that slot will be flushed out, returned back to main memory, and then put in the blocks from main memory that could be more popular than that block, the block that we just flushed back into main memory. We can do it in random way, but of course this way looks like the worst way of doing replacement policy. We can also find the optimal way by having a statistical analysis on which part of the memory that actually require more movement between main memory and cache memory. So if the demand is from that main memory that is having highest traffic, we move out the slot that is keeping the blocks from the main memory that is not so high traffic. Next scheme is direct mapping. This scheme is where certain blocks is allowed to only go to one specific slot only. If we take a block in the main memory, which slot it should go to in the cache memory system is known already. But one slot in cache memory can cater for a few blocks in the main memory, but that few block is already fixed. So we still need to resolve which block in memory that is being kept by the slot in the cache. This is also done by tagging because many blocks can go to one slot. This is done by taking again the MSB part of the address. Previously, it was only used as tag. Now, some part of it will be used to code the slot number. And the LSB is still used to address which word in the cache slot. So, for example, the previous 27-bit tag, now if we have 2 to the power of 14 slot in the cache, 14-bit is required to encode which slot is being used. What is left, 13-bit, is used to link to which block in the main memory. And of course, the remaining 5 bits is to indicate which word in the slot we are looking for. So this is how the diagram looks like. Block 0, for example, in main memory can only go to slot 0. The same to block 2 or 14 can only go to slot 0. So slot 0 can cater for 2 blocks. One slot will have many blocks that can go in, but one block can only go to one slot. So the tag now is only 13-bit because it is what is left after we minus 14 from 27. It is obvious that direct mapping does not require any replacement scheme because if a block is required, we know which slot it has to go. That slot is the one that is to be flushed. No other blocks, meaning we don't have to create a policy for replacement. Next scheme is set associative mapping. It is a mapping scheme that combines or consolidates both scheme, the associative and direct mapping scheme. The slots now are grouped into sets. The sets are now getting the direct mapping from the blocks in the main memory, but the slots in the set are associatively mapped. The link to the right main memory block location is still resolved by tagging. MSB part of the address still used as tag, and the set value LSB is still used to address the specific word in slot. Again, for example, previously we have 27-bit as tag. Now some of the bits in the tag has to be put aside to encode the set. This is how we visualize it. You can see here in this example, one set has 2 slots. Block 0, for example, is going to set 0. Block 2 to the power of 13 is also going to set 0. But which slot will keep which block, that is something that we do not know. And as you can see here, we still have 14-bit tags. And now we have to set aside 13-bit for the set. remember that sometimes we have to flush the content of the slot back to the main memory, and sometimes we have to load a new block from the main memory. There are a few ways to do it, depending on either we have to read or write to the main memory. Let's say we are reading data. Supposedly, we assume we are reading from the main memory, but now cache memory is in the middle between the microprocessor and the main memory. So let's say we are reading something. If the data is already in the cache, then do nothing, just forward that data to the CPU. But if it is not in the cache, we can either read the word that the microprocessor is requesting straight to microprocessor, then we load the entire block from the main memory into the slot, or we fill in the slot first, then we forward the requested word to the microprocessor. And if it is a writing case, if the data that we are writing is already in the cache, we can either write the data both in cache and memory, or to make it easy, we write only in the cache, and the updating to the main memory is only done when the block is flushed. We can do either immediate write or deferred write. This one was immediate forwarding of the requested data, or it's delayed until the cache is loaded. What if the data is not in the cache? We can either bring the whole block first into the slot in cache, then we update in cache, or we can just update in the memory only. And then whether or not we want to load the whole block that we are writing, we make a different decision. Because sometimes writing to a certain memory location is done only at one particular location. Next, before we go to virtual memory, let us talk about the ways we can measure how good our cache memory system is. There are two measures, the hit ratio and effective access time. Hit ratio is the number of times that the words we are referring to is in the cache. Either we are reading or writing, the word is already in the cache, divided by the total number of memory access. If most of the time the read or write is done directly on the cache without the need to reload or flush, then the cache memory system that we are having is a great system, which means we have the system to avoid long access time to the main memory, and the system is doing so well that most of the time we are accessing to a fast memory in cache memory. The other measure is the effective access time. It is calculated by multiplying how many hits we have, hits to the cache memory, and time per hit. Multiply this. This is one unit time. The other unit time is the miss time. How many times we miss, and what is the time spent in one miss. Total them up, and then we divide by the total number of memory access. Now, if our system is good, the number of hit will be very high, the number of miss will be low. A very high hit will be multiplied by a very low time per hit, added with a very low miss multiplied by a very long time per miss. If the average of this total is very low, which means we actually reduce the time that we spend reading and writing to main memory. In this case, our cache system is performing very excellently. If the effective access time is longer than the time that we spend to read or write directly to memory system, then our cache system is not doing so well. We might as well not using it. We might as well read and write straight to the memory system.